Since yp is just an assumption here, we are going to plug this yp in non-homogeneous differential equation to find unknown constants. Hello everyone, I hope you're doing great. We have already seen how to solve homogeneous differential equations, which are the equations in which the left hand side is written in a standard format with the derivatives and the coefficients, and the right hand side is 0. While this is true for homogeneous equation, this equation becomes a non-homogeneous equation if the right hand side changes to anything but 0. It could be a constant or it could be a function of x. So let's say it's a function of x, g of x. So now this differential equation has become a non-homogeneous differential equation. To solve such differential equations, we need to have two solutions. The first solution is called yc, which is the complementary solution, and then we need the second solution, which is yp, which is called the particular solution. The first solution is a result of, vaguely I would say, the left hand side of this equation, while the second solution yp would be the result of the right hand side of this differential equation. This is roughly what is going on, and yc in reality comes from the associated homogeneous version of this non-homogeneous equation, right? So what we do is, to find yc, we force this equation to become a homogeneous equation. We simply erase this g of x and place 0 instead of that. So now the same equation with the same coefficients has become a homogeneous differential equation, right? So once we do that, we solve this differential equation using a method that we have already seen, and we find the value of yc. Then we take the right hand side, which is g of x, and we use some other method which I am about to tell you is undetermined coefficients superposition approach. So this method will take the complementary solution and it will use that solution not in a direct manner but indirectly. So what we do is, let me write an algorithm for this method. The first point would be find the complementary solution yc. The second step would be assume an appropriate yp. So once we assume an appropriate yp, which is, let me write in brackets here, that it is different from yc. It needs to be different from yc, and if I technically write it correctly, I should write linearly independent on yc. Now, since yp is just an assumption here, what are we going to do? We are going to plug this plug the assumed yp in non-homogeneous differential equation to find unknown constants, right? So this method is best defined using an example. So let's do an example. This will be an exercise problem, but before I do that, let's have a look at the assumed values of the particular solution, right? So particular solution, if the right hand side of the differential equation is just a constant value, the assumed particular solution is also an unknown constant, which we will find using a method that we will see later in this video. If the right hand side of the equation g of x is first degree polynomial, like this, for example 5x plus 7, then the assumed particular solution should be ax plus b. Similarly, if the right hand side is 3x squared minus 2, which is a second degree polynomial, and there is a term in x missing from this polynomial, you will write a complete polynomial in general terms like this, where a, b, c are unknown constants. Similarly, if the left hand side is third degree polynomial, you will use a third degree complete polynomial. If the right hand side of the differential equation is sine 4x, you will use a complete version of both sine waves, which is cos and sine, and there will be unknown constants a and b along with each of these cosine waves or sine waves. So cos 4x will also have the frequency 4 will not change in both of these things, it will be the same. If there is 5x over here it will also be 5x, right? So if there's an exponential function on the right hand side, exponential function is the g of x, then the assumed particular solution will be, which we also call it the trial particular solution, would be a e to the power fx. Again, the speed of this exponent changing, which is 5x, is the same in the assumed solution as well, but the constant is different. After this, all you look at is the variance of all of these 7 parts. If there is a combination of a first degree polynomial and a sine wave, you are going to combine both of these by multiplying them. Now we know the trial particular solutions, so let's do an example. This is exercise 4.1, problem number 1. So the equation that is given to us is y double prime plus 3y prime plus 2y equal to 6. So the first part is that we need to find the complementary solution. So we write down the associated homogeneous equation of this non-homogeneous equation, and in order to use the method of constant coefficients for homogeneous equations, we need to write the auxiliary equation, right? The auxiliary equation for this would be m square plus 3m plus 2 equal to 0, and the roots for this equation would be minus b plus minus b square minus 4ac divided by 2a. So the roots are minus 3 plus minus 1 divided by 2. So the first root would be minus 3 plus 1, which is minus 2 over 2, which is equal to minus 1, and the second root would be minus 3 minus 1, which is minus 4 over 2, which is equal to minus 2. So now we can write the complementary solution in general form as c1 e to the power minus x plus c2 e to the power minus 2x. So now we go to the table and we see that if the right hand side is just a constant, we know that the assumed particular solution based on this constant should be a, which is just an unknown constant. So we use that and plug that value of yp into the given differential equation and then compare the coefficients, right? So if yp is equal to a, yp single prime would be equal to 0 because derivative of a is 0, and yp double prime would also be 0 because derivative of 0 is 0. So now let's plug in the values. 0 plus 0 plus 2 into the particular solution y, which is a, equal to 6. So now we have to compare coefficients. So if this is a coefficient of some constant 1 multiplied by 1, and this is also being multiplied by 1, this coefficient can be compared with this coefficient. And in this particular example, there is not really need to compare the coefficients because it is already very simple, and you can simply solve this equation to find that a is equal to 3. But just to give you the conceptual idea, because in more complex examples you may need to compare the coefficients for different types of functions. So now we write the particular solution based on this, and the particular solution is equal to 3, right? So now the general solution y of x can be written as c1 e to the power minus x plus c2 e to the power minus 2x plus the particular solution 3. And now this is our general solution for this non-homogeneous differential equation. So if you were given the initial values, you could find the values of c1 and c2, but this is the first method that you have seen so far where you can directly solve a non-homogeneous differential equation. I hope you understood this concept, and I hope you liked the video. So please subscribe to stay in touch, and I hope to see you in next videos. Bye bye.